So my name is Darren Graham. I'm from the University of Manchester. I'm a reader, which no one actually understands what that means. It's one of those British titles. It's kind of equivalent to associate professor. Okay. So Manchester, you probably... this is not working. Let's see if I can work out how to get to the next slide. So Manchester, you probably know where it is due to a couple of football teams that I won't mention. But if not, it's in the northwest of England, about 1 hour from the Irish Sea, just east of Liverpool. I won't discuss their football teams either. And the university is a city centre campus university, and it's just south of the city centre of Manchester. And we have about 40,000 students and just under 13,000 staff. And physics at Manchester is actually the largest undergraduate physics department in the country. Our first year intake is about 330 students this year. Now, I work both at the University of Manchester, but also just down the road at the Cockcroft Institute of Accelerator Science and Technology. So I use both accelerator facilities and lasers. And at the Accelerator Institute, we have various linear accelerators. This is Clara, which is a 35 mega electron volt accelerator, and it's currently being upgraded and renamed Phoebe, which is going to be a 250 MeV machine. So most of my work is not really in this field of spintronics. Most of my work is actually in the field of terahertz acceleration. So I like to use terahertz radiation, laser-driven sources for a range of applications in the accelerator environment, both from pure acceleration, but also we are interested in things like diagnostics of electron beams by using streaking experiments, and also characterization of accelerating structures like waveguides. Now, I probably don't have to tell you why Spintronics is an interesting source, but it is an interesting source for us in terms of the accelerator environment. In terms of why it's unique, if you look at the four kind of key characteristics, I'd say, which is high electric field, large bandwidth, gapless spectral coverage, and also low pulse energy for excitation. The Spintronic source is the one that actually fulfills all those requirements. So we started out being interested in the Spintronic sources because of the fact you could manipulate the polarization profile in the emission. It's actually quite good for a number of reasons, one is which is characterizing waveguides, because you can create some interesting polarization profiles. And some of the early work we did was back in 2019, where we showed that if you take a simple bilayer structure, a permalloy platinum structure, and you apply more of an interesting magnetic field pattern by flipping your magnets to opposing, say north-north, you could generate this interesting kind of quadratic profile in the terahertz polarization. And what you can do with this is you can then tightly focus it and generate an on-axis longitudinal component to your electric field. But what I want to talk about today is kind of two things. I was originally going to talk about just exploiting magnetic anisotropy and what you can do with that. But when I saw the kind of discussions of the CW as well, I thought it might be interesting to sort of talk about some recent work, which is where we've produced tunable narrow band emission from a spintronic emitter. So you can produce very narrow line width and you can tune it across the spectrum. So I want to talk about that today as well. So first of all, magnetic anisotropy. I'm going to show how you can actually enhance this in the deposition and actually use that then, exploit it to get field-free emitters, and also you can exploit it to get polarization control from varying the applied magnetic field strength. So all the structures we're going to look at are going to be the very simple structures you're all talking about. Cobalt, iron, boron, platinum, or the tri-layers with tungsten, those structures. There's nothing been engineered into the structures, okay? So where do we start? We started with depositing bilayer structures of cobalt, iron, boron, platinum. And we were interested in the cobalt, iron, boron because we knew from the literature, from the magnetic characterization work, that there was a report of a uniaxial magnetic anisotropy in these films under certain growth conditions. So we thought we'd take a look at our samples. We deposited these on fused silica, and then we cut out from those deposited samples an 8 millimeter diameter disc. And the reason for making a disk is to remove any edge effects. You don't want any shape anisotropy contributing to the measurements. So we produced these disks. We put them in a magnetic field. We applied a saturating magnetic field, in our case about 40 millitesla. We measured the terahertz emission, which is polarized perpendicular to the applied field. We then removed the applied field and measured in the remnant state the terahertz emission. And then we rotated the sample azimuthally and repeated the process, applying the saturated field and removing back to remnants. Okay? And we did that in 10-degree steps over the full 360 rotation of our emitter. And under magnetic saturation, you see what you'd all expect. It's independent of the azimuthal rotation of the sample. Okay? However, in the remnant state, it reveals what's often kind of not seen is this, there is an azimuthal dependence. And what it actually reveals is that this uniaxial magnetic anisotropy, we can see there's a hard axis and an easy axis in the structure. And what you see along this, what we call the easy axis, is that when you remove the applied field, the terahertz emission drops to about 87% of the peak value you had under saturation. And along the hard axis, it dropped to about 45%. So we observed it was existing in our films. So then the question is, can we exploit that? Okay. So, actually, I should mention as well, we also applied the magnetic field to measure the hysteresis loops. And again, you can see along the easy and hard axis, the kind of expected square shape you would get from an easy axis and the kind of diagonal from a hard axis. And you see the same in the VSM that matches the terahertz emission. It just convinces you there's that relationship between the terahertz emission and the magnetic properties. So how did we exploit the UMA? How did we enhance it? We didn't apply magnetic field during growth. It wasn't required. Instead, we used the fact that you can actually adjust it by changing the rotation speed during deposition and also where you place the sample. If you go for an oblique deposition geometry, you can actually enhance the effect as well. And so we grew a series of films under these different rotation speeds and positions in the reactor, and they look very similar. The subtle differences here we've explained due to differences in layer thickness. So we did some X-ray reflectivity to account for that. But if you then measure the terahertz signal under saturation and the terahertz signal remnants, you can make these graphs. And what this is, it's a plot of the remnant signal divided by the saturated signal. Okay? And you can see this variation here when you're on the easy axis, on the hard axis. So when you're on the easy axis, you remain your signal close to the saturated value. On the hard axis, you see the reduction. And we wanted to try and maximize that difference. So first of all, if you change just the location of the sample in the reactor, you can see you can make a significant difference to that. If you turn off the rotation as well, you can make a difference to that. Okay? So you can control the degree of the uniaxial magnetic anisotropy. And so we can produce a sample where we've maximized that. So let's look at that sample now in a bit more detail. So this is the sample. You can see the terahertz emission. In blue here is actually the saturated field aligned along the easy axis. And then we take the field away, and it remains at about the same level. It remains at about 98% of the saturated field value. However, if you rotate the sample azimuthally, apply your field along the hard axis, you can see you get the red curve the same. You take that field away, and now you see the reduction. It drops to about 16%. Okay? That's our enhanced UMA. And straight away, you can see that actually you've got a sample here that you can remove the magnetic field, and it remains the same emitter, effectively. There's no need for that magnetic field anymore once you've pre-aligned it. So how well does that last? Well, we thought we'd try. We used a moderately high pump fluence, about 1.6 millijoules per square centimeter. We kept the sample continuously illuminated, and then we took measurements every hour. So at the beginning, you can see we initially saturated it, measured the emission, and then every hour we took a spectrum under continuous illumination, and it stayed about the same. The fluctuations you're seeing here is actually we attributed to the laser power fluctuating. If we normalized for that, you can see it's relatively constant. We even then turned the laser off overnight, came back to the next day, turned everything back on again, and measured 28 hours later, we're still seeing the same signal. There was no need to reapply the magnetic field. It remains stable under this excitation fluence. Now, in all these experiments, we were using 100 frames per second pulses, thick electro-optic detection crystals, so you don't see the bandwidth. However, these structures do still have the bandwidth. If we go to a shorter pulse duration, 20 frames per second, a thinner crystal, 100 microns, you can start to see that bandwidth appearing. Okay, so the emitters still have the bandwidth if you drive them correctly. But you can also use the hard axis. If you rotate the sample azimuthally, now you've got the hard axis where you do see this reduction, you can actually use it to rotate the linear polarization. So here, this is our sample with the most defined UMA. We align along the hard axis, apply our saturating field, you get the linearly polarized emission perpendicular to the applied field, and then if you turn down the magnetic field, you get the rotation back as the magnetization, the magnetic moments are kind of rotating back to the z-axis, you get the rotation of the linear polarization. So you've got polarization control as well. The one thing I'd like to point out, though, is if you have a sample with a weakly defined UMA, you actually get quite a complicated emission in the polarization spectrum. Sometimes it can look slightly elliptical or even more complex like this when you don't apply the field. So you have to be a little bit careful what you're looking at. And you'll see that as well in phase shifts between the two polarized components. Now, the other thing to talk about today is something that's quite recent. It's accepted and now in press in Applied Physics Letters, so it should be out very shortly. And that is that we can produce multi-cycle pulses of terahertz radiation with a narrow bandwidth, and we can tune that across the spectrum. And we do that using what's called a chirp pulse beating scheme, which I'll explain today. And really, we use that as a proof of principle to really pave the way here to use these spintronic emitters to have sources that are narrowband and tunable across the entire spectrum that you can get from these devices. So there's nothing, again, done to the emitter. Here, this is just the standard tri-layer emitter, tungsten, cobalt, iron, boron, platinum. It's just how we drive that emitter that's slightly different. So how do we do this? Well, what we do is we use an interferometric recombination of chirped pulses. So you take your laser pulse and you chirp it, okay? And the simplest way to do that is if you're using an amplifier system, you just detune your compressor so you've not got your transform limited pulse, okay? So that's what we did. We detuned our compressor, we had a positively chirped pulse, and then we used an echelon structure. Now, you could use a Michelson interferometer. There is benefits in using an echelon, however, because you can actually utilize more of the pulse energy for pumping, so we went in this direction. So what is an echelon? It's a high reflecting mirror, 0 incidence normally, and a partial reflector, which was about 38% reflecting. And so when this chirped pulse comes in, you get a series of reflections, and you'll get a time delay between all those reflected pulses, which is governed by the separation between those two optics, okay? And what that leads to, when you get that recombination of all those pulses, you get a beating in the intensity profile of the exciting pulse. And the frequency of that beating is just given by the time delay between the pulses, governed by your separation, and the pulse duration of your transform limited laser, and the pulse duration you've chirped it to. These are the key control parameters. So this is the setup. So we're using here just a 1 millijoule amplifier, 1 kilohertz, 50 femtoseconds, and we detuned the compressor to get us either 6 picosecond pulses or 12 picosecond pulses, full width half max. First of all, I'm going to talk about the 6 picosecond data, and then we take that onto this echelon, and then just straight onto a standard spintronic emitter. There is a magnetic field here, but it's vertical, the way the arrangement was set up. We separate out the terahertz from the residual pump light using a combination of indium tin oxide coated glass and high resistivity silicon. And then we focus that onto a zinc telluride crystal for electro-optic detection. And we used a 0.5 millimeter thick crystal here, so quite a thick crystal. Now, the one thing you have to do then to measure with electro-optic sampling, you need your short pulse, okay? So you have to introduce a grating pair compressor here to recompress the laser pulse back from 6 picoseconds to your 50 femtoseconds. And then we do electro-optic detection often in a back reflection geometry. There's no real reason not to use a transmission. We prefer the back reflection. Often we prefer it just because you've got independent control of the focusing of the probe and the terahertz. Because if you do it in transmission, often either you're drilling a hole in your parabolic mirror or you're relying on that parabolic mirror in your focusing geometry. So we prefer this kind of approach often. Before I show you the multi-cycle data, I want to mention one complication, and maybe the reason why we use the thick electro-optic detection crystal is we're measuring multi-cycle pulses. These are long pulses, so we want to remove the reflection artifacts. And so if you look at the single cycle emission first, you take out the partial reflector from the echelon. You can see the reflection pulse here, which is associated with the fused silica substrate we used on the Spintronic emitter. And we can do a very simple approach to remove that reflection mathematically. We can just take the measured signal as just the sum of the electric field with a reflected pulse which is delayed and reduced in amplitude. You can Fourier transform this and divide it by this 1 plus r e to the minus I omega tau. And you do that and do an inverse Fourier transform, you can get back to this corrected spectrum. And it helps remove these Fourier transform artifacts from the frequency spectrum. Okay. Now the reason we have this narrow bandwidth is because we're using quite a thick electro-optic detection crystal because we didn't want the annoyance of the reflections. Okay. But if we then go put the partial reflector mirror back in, we now have our echelon. We then see all of a sudden we get these multi-cycle emission. And you can tune that echelon gap from about 42 microns to 232 we went to, and you can start to tune the terahertz emission. You could keep going. Really, we're governed by this bandwidth that we're using, so our thick crystal, our long pulse laser, but there's no reason why you couldn't use thinner crystals, 10 femtosecond lasers, and just continue to tune this. Okay? Now, there's a few features in the spectrum worth noting. First, you start seeing these other pulses as you go to higher frequencies. This is actually a reflection artifact still. So it's when we haven't got perfect reflection removal. We've still got a little bit of this Fourier transform artifact you're starting to pick up. And these other pulses here, these are second harmonics. And it's well known that you get these if you use an echelon, because you've got these multiple reflections. You will get harmonics as well in the intensity modulation of the driving pulse. Okay. If you use a Michelson interferometer, you wouldn't get them, but you wouldn't have as much pump energy, okay? Because you'd only use 2 pulses, with the echelon using the whole train of pulses with time delay. So you might ask, well, what does it actually look like? Because what I showed you previously, if I just go back, it's all normalized data to look at the line widths, really. But what does the raw signal look like? Well, this is the single cycle emission you're all used to. When you put the echelon in, you get a slight reduction here. It's not surprising. You're broadening out the pulse from 50 femtoseconds out to 6 picoseconds. So you're going to get a reduction in the peak field that you're pumping with. And you can see it tunes following the kind of envelope of this. Okay? And you can see the harmonics a little bit more clearly here on this scale. Now, one thing you've probably noticed is this width is changing. Okay? We actually see it changing from about 128 gigahertz to about 287 gigahertz at 2.3. And this is because in chirp pulse amplifiers, it's very common to have third order dispersion. And what that does is it gives you a curvature in the chirp. So you don't have this idealized linear chirp on your laser pulse, where you have your red components ahead of your blue. You've got this quite strange curvature to it. And what that means is, it means that this beat frequency actually varies across the duration of that chirped pulse beating output. Now, we modeled this, okay, in the emission, and we got pretty good agreement. The little exceptions here are really because of that annoying Fourier transform artifact, slightly distorting the measured line width. And the reason it's varying is, again, because you have to add in this additional chirp pulse beating intensity modulation because of that third order dispersion. It's common in these systems. If you get rid of that, this would be a constant, and it would be about 107 gigahertz. So can we get rid of it? The answer is yes. There are techniques to do that. You can actually play around with the relative spectral phase of the chirp pulses. and that's been shown in the literature, you can use a second grating pair to eliminate that curvature in the chirp as well. So there's no reason why you can't keep the emission narrow. There's no reason why you can't tune it with the echelon separation. But we wanted to show what was possible if you went to a larger chirp pulse, and you can pull the line width down further. Because the line width, when you remove this additional third-order dispersion term, it's really just dependent on the extent to which you chirp the pulse. So if you chirp from 6 to 12, you can bring the line width down by nearly a factor of 2. So we actually show that you can, if you go to 12 picosecond chirp pulses with the echelon, you can get down to 41 gigahertz. You can see again the second harmonic features, and you can see the nice multi-cycle pulse that can be produced. So, in summary, I just wanted to highlight today some potential ways of exploiting spintronic emitters. Very simple devices that you all already have. You can enhance the uniaxial magnetic anisotropy to make emitters that are quite stable under high fluence, that don't require the magnetic field any longer. You can use the hard axis to give you a polarization control with no moving parts. And you can use a chirp pulse beating scheme if you want narrowband tunable terahertz pulses from the spintronic emitters. So I'll just finish by showing you a review article from our group, and thank you for listening.